wanted to start off by thanking Josh and Jeannie and team for allowing Intel to be up here and for your forbearance, having a hardware geek sort of open up the event. I've worked for a couple of different kinds of technology companies, and I remember every time we worked for a software company, we wanted to run on all kinds of hardware. We didn't want to sort of focus on any particular kind of hardware. And now that I work for a hardware company, we want to talk about, you know, hardware technology and how it's a benefit to software, so it's a constant kind of a thing. So I appreciate the opportunity to come up here and talk to you a little bit about some recent technology that Intel introduced that's having a particularly interesting effect on databases. Before I get started, I just want to ask the room for a show of hands. If anyone's here heard of Intel Optane technology? Okay, and the Intel Optane persistent memory as well. Okay, so I'll try to go through that part of the presentation a little bit quicker, I guess. But for those of you that might not be familiar with what Optane is, or even if you're familiar with Optane, Intel put together a kind of a cheesy video that has a pretty good description of what the technology is. So without further ado, let me go ahead and load that video up.
Design a next-generation non-volatile memory called 3D XPoint, something many experts said was impossible. And this new technology isn't just twice as fast, or even 10 times faster than NAND. It's up to 1,000 times faster. So how'd we do it? To make 3D XPoint inexpensive, we needed to pack lots of capacity into a tiny footprint. We started by slicing sub-microscopic layers of materials into columns, each containing a memory cell and selector. Then, we connected those columns using an innovative crosspoint structure consisting of perpendicular wires that enables memory cells to be individually addressed by selecting one wire on top and another at the bottom. We can stack these memory grids three-dimensionally to maximize density. And whereas DRAM requires a transistor at each memory cell to access or modify the cell, making DRAM big and expensive, each 3D XPoint memory cell can be written to or read by simply varying the voltage sent to its selector, completely eliminating the need for transistors. This simple, stackable, transistorless design enables 3D XPoint to pack up to 10 times more capacity than DRAM in the same space, greatly reducing cost. When it comes to memory performance, low latency is the key. Whereas NAND latency is measured in tens of microseconds, 3D XPoint technology's latency is measured in tens of nanoseconds, a tiny fraction of NAND's wait time. This makes 3D XPoint ideal for high-performance SSD storage, delivering up to 10 times the performance of NAND across a PCIe NVMe interface. Plus, 3D XPoint technology's lifespan is not significantly impacted by how many write cycles it can endure, which means it can simultaneously serve as a single, high-speed, high-capacity pool of system and storage memory. There you have it, a truly disruptive memory technology that's fast, inexpensive, and non-volatile. Get ready to unleash your processor's true potential and realize possibilities we thought were decades away. So be sure to stay tuned for upcoming announcements on 3D XPoint technology.
So on April the 2nd, we actually made a second announcement on 3D XPoint. By the way, I want to try to see if I can find that job and get that job that guy has, just narrating videos with that sort of cheesy voice that he has. I thought that'd be kind of cool. The presenter there talks a couple of things about Optane technology, but with this slide up, I just kind of want to emphasize a couple of them. So the very first thing Intel did with this, and by the way, they mentioned the name, the trademark name is 3D XPoint Memory Media. This was a joint development effort between Intel and Micron. Intel's iteration of 3D XPoint Memory Media is referred to by the Intel brand name Optane. So anytime you see Optane, that's 3D XPoint Memory Media technology from Intel. So the very first thing that Intel came out with was an SSD, right? It was, in comparing it to the existing NAND SSDs in the marketplace, there were some remarkable differences with the Optane SSD. One of the things was that because this technology is bit addressable, the Optane drive doesn't suffer from write amplification, right? Every time we write to a NAND device, there's background activity that needs to take place to sort of sequence the write and get rid of the old block. In Optane world, you change the bits right on the media. So as you add write activity to a NAND drive, you'll see read latency tends to go up. And with Optane drives, read latency remains flat throughout. So not only is it a faster drive, but it also doesn't suffer from write amplification. And the second thing that he did mention in that little video is that everyone here familiar with the notion of NAND drives and something called drive writes per day, the endurance of the drive? If once there's so many writes to the NAND material, it will go into read-only mode and you won't be able to write to it anymore. That's the endurance factor of these drives. So the normal NAND endurance is measured in like 3 drive writes per day, a single digit. The Optane technology measures out at around 60 drive writes per day. So the endurance of this material is much, much higher. And so Intel introduced it as an SSD in 2017, and then at sort of the beginning of this year, on April the 2nd, to coincide with the introduction of a brand new, our next generation Xeon processor, the server processor, Intel introduced Optane in the form of persistent memory. So this is a memory DIMM of this Optane material, right? So I'm aware of the fact that persistent memory isn't new in the industry. But in this iteration, Intel has sought to kind of kick off a development, sort of a enterprise-wide or ecosystem-wide development effort around the standardized persistent memory programming technologies, methodologies, around, in Intel's instance, this Optane persistent memory. So what it means for the programmer, of course, is that in the past, having to choose between speed and DRAM and reliability, typically disk, now there's a third path, there's a third tier of storage that is on the memory bus but is persistent. All right, so this is a picture of what the Optane data center persistent memory module looks like. It looks very much just like a DIMM. It goes into a DIMM slot. And there's a couple of things that I'd like to point out at the outset here about the Optane persistent memory. It shares the DIMM slots in a server. So in order to put Optane memory in, you have to not populate it with DRAM, right? So the DRAM and the Optane DIMMs share space in the server. So what we're beginning to see in terms of a lot of development efforts is adding this Optane memory pool and then doing something different with the Optane memory pool than what you do with the DRAM memory pool. The other thing about Optane data center persistent memory is the sizes. So the sizes for Optane data center persistent memory at launch are 128 gig, 256 gig, and 512 gig in its sizes. It's also designed to be priced to be less than DRAM. Now we know that the DRAM market is pretty volatile, so this is something that Intel actually is going to be visiting on a quarterly basis to make sure that there's a value for using Optane persistent memory in a server. The other thing about Optane in terms of its use in a server is there's 2 modes of operation. So the first mode that I want to talk about is the least interesting one. It's the one on the right there, called memory mode. In memory mode, the Optane DIMMs operate like a volatile memory pool, essentially. What happens is that when the server comes up, the Optane DIMMs, whatever capacity you have there, are reported as system memory. You don't actually see the DRAM as system memory. And then the memory controller on the CPU, in conjunction with the Optane DIMMs, use the DRAM as a write-back cache, right? So one of the things about memory mode is you have to make sure that you have the proper amount of DRAM for your write-back cache for your application workloads. Now, the kind of point behind memory mode was to provide this technology in a way in which you wouldn't have to alter your programs. You just run your regular programs the way they are on this server. So the value of memory mode is essentially being able to put a lot of memory in a server for less than the price of equivalent DRAM memory. That's the basic selling point behind memory mode. Personally, I think it's kind of one of those things that I imagine the product management team felt like we have to put something, we have to develop a mode for using this technology for people to use it without having to have access to developers or whatever. But I think it's going to be a sort of a short-lived value of this persistent memory product. The more longer-term one, the more interesting one to me, is what we refer to here as app direct mode. And in AppDirect mode, when the server comes up, it will report both memory pools available. A persistent memory pool, which is the Optin memory, and then the DRAM pool. Then it's up to the application developer, the person who's writing the program, to use the memory pools for whatever they would like to use them for, with the knowledge that the persistent memory pool is persistent and the DRAM memory pool is not. By the way, in memory mode, it is true that the memory that gets written to these modules is persistent, but since they're encrypted in memory mode, what happens when the server reboots is it throws away the encryption, it creates a new encryption key, which basically, treats the memory as volatile. So that's why it says in memory mode, a volatile memory pool. So memory mode operates just like regular DRAM memory from that perspective. In terms of AppDirect mode, I think one of the neatest things about putting this persistent device on the memory bus is that you don't have to do any paging, context switching, interrupts, or kernel code executes. So it's very, very fast. It also supports not only DMA, but also RDMA. And so what we've begun to see, and certainly database developers are not the only ones who have begun taking advantage of this new technology, this new capability, but we started to see some very interesting use cases amongst some of the database developers. And I just kind of wanted to highlight a couple of them. So in the case of SAP HANA, with their update, as it's mentioned there, SPS 03, they've used the persistent memory pool in an Optane data center persistent memory server to store the columnar store, so they don't have to load that from disk at startup. So basically, the value in this particular solution is on restart time. So in using persistent memory now, as opposed to disk, for an SAP HANA restart time have dramatically improved that. I think one of the tests that we ran, it took a 40-minute restart time or 50-minute restart time down to 3 or 4 minutes. So it was a dramatic improvement. Aerospike is another example that used this for the very same effect. Using AppDirect mode to use the Optane persistent memory to store their index. And as a matter of fact, the quote there under solution, the second bullet point under solution from Brian Bolkowski kind of describes what they're doing. By using a persistent layer for their indexes, the full restart of Aerospike is possible without a primary index rebuild. So those are two kind of similar examples of using this persistent memory pool in kind of a new way. In terms of Spark, what we were able to use the data center persistent memory pool for, the Optane memory pool for, was to create an OAP cache that would allow the hits to come from the DCPMM memory as opposed to coming from disk. Again, moving stuff into this persistent memory that's on the memory bus and allowing the application to take advantage of this. And in certain instances, it allows a bigger build, a bigger node, and in some instances it increases performance as well. So there's been some interesting kind of effect by doing this. This is very similar, by the way, to the work, and by the way, much of the work that I'm talking about here is done either with Intel Engineering's contributing to open source projects, or Intel Engineering working with different industry software vendor engineering teams themselves. All of these slides are from the Intel Engineering teams that were provided to me. By the way, I apologize for the kind of a font mismatch. So one of the things that the Intel Engineering team that's been contributing to HBase realized that when they tested straight memory, DRAM, and DCPMM memory, remember it can, depending upon the transaction, the Optane persistent memory can be slower than DRAM. Right, that's the reason that both still exist in the server. But found out that in the testing that they had done with a 1.2 terabytes of hot data fitting into both DRAM and also into the DCPMM both bucket caches, that the performance was very close, right? So this is kind of one of those use cases in where if you can use the persistent memory for some part of the program and your performance is close enough, you can actually receive a benefit from that, right? So it's not the same performance. You see anywhere from 95 to 97%. But the reality is that you can create a larger bucket cache with the DCPMM memory. Remember that the DIMM sizes are larger. They're much larger than the ones that exist in DRAM in the industry today, 128, 256, and 512, and they're priced to be less than DRAM. So in the testing and the work that they did, enabling HBase, the HBase bucket cache for DCPMM support, found that you could actually increase the throughput, particularly in the test that they ran with 50%, comparing a 50% data in DRAM cache to a 75% data in DCPMM cache, that almost, not quite 1.5 times throughput performance by making this change. By the way, this bucket cache optimization for DCPMM, I believe, has been pushed out to the open source community. And if you guys, if anyone in the room is interested in hearing a little bit more specifically about this work, please feel free to email me. My email was on the very first slide, just my first and last name, jason.lam@intel.com. And I'd be happy to put you in contact with the engineers. They would have come out for this presentation today, except that they had exceeded their T&E budget and they happen to actually be in India. So, but be happy to put you in contact with them if you guys have any questions specifically about the results that they achieved. The last thing I kind of want to touch on here before closing is other ways of using this technology. So I mentioned that AppDirect is the persistent mode of Optane persistent memory. Memory mode is not persistent. But AppDirect has one other unique ability, and that is the ability to appear as a drive. We call it storage over AppDirect. So it isn't entirely accurate to say that in order to use AppDirect, Intel Optane persistent memory in AppDirect mode, you need to rewrite your program. That's not entirely true, right? If you use the AppDirect mode of the modules in storage over AppDirect mode, they show up as a drive, right? And in this test with KDB that we did, we simply used that aspect of the storage over AppDirect mode, and they used it to load up a bunch of their historical data in their particular application, which provided them with better performance. For those of you that don't know, KDB is an FSI, a financial services industry database, and a lot of the people that use it are looking for historical data oftentimes, and the request for historical data will oftentimes hit disk. So in this case, the disk is the Optane module on the memory bus. And then you can see the performance improvement that was gained by that. Now, the last kind of, I think, to me anyway, interesting use case of the technology is just a test that was done, right? This isn't necessarily a database test. It was simply a test that Intel engineers did using DRBD, right, the distributed remote block, is it duplication? No, with the last D. And RDMA to do copies from one Optane DIMM to another without going through the CPU, right? And so I thought that was a pretty cool use of it, and kind of an indicator of what might be possible kind of going forward into the future. And so I think that persistent memory has you know, sort of, by Intel coming out with persistent memory in 2019, has making an attempt to kick off, you know, kind of a renaissance in terms of, or a look again at the way in which these programs are written, with the notion that you've got now a third memory tier. It's not quite DRAM and it's not quite disk. It sits between. So the performance is in between. It's persistent technology in AppDirect mode. And it also has some very interesting and unique capabilities. And we're just starting to see some of this stuff kind of come to fruition, right, in projects like HBase and some of the other ones that I mentioned. There's also a whole bunch of resources out there, both in the open source community as well as Intel, available at Intel, to help developers, you know, start getting involved in this particular project. And so I don't know if anyone had any questions at all of anything that I presented so far. Yes, sir. So the question was, will a slide deck be available? And I absolutely can make that available to the organizers. I'll get with Jeannie and Josh and make sure that you guys have a PDF of these slides, so you have all these URLs and everything like that. Okay. By the way, if you couldn't tell, I'm not a programmer, right? But I subscribe to the Gmail persistent memory group, you know, get the mails from there. And there's a fair amount of activity that's going on there. Some persistent memory conferences that are going to be organized, probably in Silicon Valley, But it seems like it's going to be a very interesting 2019 going into 2020 with this technology. I think some of Intel's sort of stated direction for future iterations of this product is to improve speed, improve capacity, and so you'll see that there'll be some kind of interesting servers being built in the world. The last thing I'll say before closing is that the one downside, I think, of the technology is it's only for the new servers, right? So people that have existing Xeon servers wouldn't be able to populate their servers or take out DRAM and put Optane memory in. It's only for what Intel's code name for the Xeon processor is called Cascade Lake, if anyone's familiar with that. It supplanted Skylake as the second generation Xeon scalable processor. So that's kind of, I think, one of the downsides of Intel's iteration of it. They updated the memory controllers in the Cascade Lake CPU, so it does require that CPU in order to use this technology. But some very cool first looks at some of this stuff, and we're really excited to work with our friends at Cloudera and the friends in the industry to see where we can go with this. I know one thing, as I mentioned, I've worked for a bunch of different companies. Every time a company even a company as big as Intel comes up with this idea, they think about and they write these presentations internally and say, you could use it for this and you could use it for that. The marketing team and the engineers we think we could use it for this, we think we could use it for that. And the reality is that I don't know that they sort of really even understand what it can be used for until it gets into the hands of folks like yourself. It's really the developers, the community that really start to take this technology in a very interesting way. So I think we're just sort of at the beginning of some pretty interesting stuff going forward. Okay? So thanks for your forbearance for the hardware geek. And I turn it back over to, Mark.
Yeah, just a question.
Okay.
What type of degradation do you see with Optane versus DRAM?
So that's a great question. The question was, what kind of performance degradation do we see between Optane memory and DRAM? I'm going to sidestep it a little bit and say it depends upon what you're doing. But in general, because you saw there with the bucket cache, we were able to get about 95 to 97% of performance there. If you're doing a straight benchmark, you'll typically see the Optane memory operating anywhere from 1/4 to 1/5 the speed of DRAM. And that's a mix of reads and writes and things like that. So that's kind of what the initial testing has indicated to the Intel engineering team. When they gave us our internal engineering training, that's how they described it. But again, the really interesting thing about this, and the HBase optimization was a classic example, it depends, your mileage will vary because it depends ultimately how you're going to use this technology, what kind of I/O activity you're going to send to it, et cetera, et cetera. So I was surprised when I saw the HBase information being forwarded to me by the engineers that they were able to get very, very close to DRAM performance for the bucket cache. So, but in general, when they run the benchmarks, 1/4 to 1/5 we're seeing. And by the way, I think that's one of the things that they want to improve going forward in the next gen and so on, is to continue to up the performance. Okay, but good question, Mark. Okay, all right. I will turn it back over to Josh. Okay, thank you, guys.